Log on, tune in, find out. Another good idea from Cambridge.
Guillaume Bal from Columbia University. There's a theme in a way emerging in multiple physics here. Either, as Simon mentioned, multiple physical processes that are independent or coupling between physics. And so in that case, it's appropriate that Guillaume's going to talk about multi-physics inverse problems and internal functionals.
Okay, thank you very much. Thank you to the organizers for having me here. So, as Bill mentioned, this is a follow-up on what Simon just presented in optics to a certain extent. It's also a follow-up on what Li Hong talked about in about photoacoustics yesterday. Now, from the mathematical point of view, what I'd like to insist upon is inverse problems where we have internal functionals. And that looks like a real inverse crime, as opposed to the inverse crimes related to numerics. When we do an inverse problem, typically we don't want to be intrusive. And internal functionals typically don't come that easily without being intrusive. And yet now there are new modalities, those hybrid imaging modalities, multi-physics modalities. There are several names for the same concepts. There's new modalities that allow us to mathematically obtain internal functionals. And once we have obtained those functionals, we still have to look at the inverse problem. And this is this class of inverse problems that I would like to talk about here. So before we look at the why we need those hybrid inverse problems, multi-physics inverse problems, multi-wave inverse problems, those are the three names that are being used at the moment for to describe them. Let's look at the Calderon problem, where what we want to reconstruct is an unknown diffusion coefficient. It's the same thing as in optical tomography. If we assume that there's no absorption, we neglect absorption for the moment. So we're interested in measuring a diffusion coefficient. You send light into tissues. You might see that light propagates. There's a little bit of red glow. So you send photons into tissues, or you send electrical currents into tissues. You measure the outgoing density of photons or electrons. And from this information, which is all possible informations you can acquire at the boundary of the domain, you would like to understand whether you can reconstruct gamma. And the reason why we want to do this is what Simon mentioned in the previous talk. Gamma displays relatively high contrast. Healthy tissues, not healthy tissues have different gammas. And that's what we care about. There's two things we care about in an inverse problem. One is contrast. We want to see something of interest. And second is resolution. We want to actually see it at the typically millimeter or submillimeter scale. Okay, so optics and EIT, electrical impedance, are useful mechanisms because they give us high contrast. Unfortunately, this problem, which consists of reconstructing gamma from all possible Cauchy data at the boundary of the domain, this is an ill-posed problem. It's an injective problem, which is still relatively interesting. There is a uniqueness result. If you acquire all possible data, then gamma is uniquely characterized, which is a very good sign and an important sign even in applications. All medical imaging techniques involve operators that are injective, the ones that work. So we have this injectivity. However, we don't have the resolution. And a proxy for resolution, which I'm going to use here, is the stability result. So the stability for the Calderon problem is so-called logarithmic. And if you have two possible diffusion coefficients, gamma and gamma tilde, that are possible for your setting, and if you assume that you have made all these possible measurements for the conductivity gamma, let's call that measurement operator applied to gamma. Now, if you have another set of measurements, multiple operator applied to gamma tilde, let's look at this difference as noise. If noise is present in your data, and it turns out that noise is in the range of the operator, of the measurement operator, then you have a certain error, and you would like to understand how this error propagates onto your reconstruction. And this inverse problem is ill-posed in the sense that noise is tremendously amplified during the reconstruction. So So these stability estimates, which are considered to be relatively optimal, maybe the delta is not completely optimal, what they say is roughly the following. If you have made an error, which is experimentally of 10 to the negative 10, say, you take the log, that's minus 10. You take the absolute value, that's 10. You take minus 1, that's 1 over 10. An accuracy of 10 to the negative 10 on your measurement, which is almost impossible in practice, gives you only a reconstruction, which is 10% accurate. Okay, so the tremendous increase of noise during the reconstruction makes that this problem lacks resolution. The high frequency components are essentially destroyed during the forward propagation of the photons. That's what we saw in Simon's talk. So this problem is good because it has high contrast. It's not so good because you've lost resolution. Now, as I said, a good inverse problem in medical imaging has to have both. It has to have high contrast, but it also has to have high resolution. Where do we get contrast? Optical tomography, electrical impedance tomography, elasticity are typical material properties that display very high contrast between tumors and healthy tissues, say. Where do we get resolution? We've seen modalities yesterday in the afternoon. What are the high resolution modalities used in medical imaging? It's ultrasound, it's MRI, it's Array-CT. Now, a reason why they have high resolution is often because they are low contrast. The high resolution typically comes because there is low scattering. Scattering typically comes with low contrast. That's the case for ultrasound. Ultrasound is very high resolution, but it is typically low contrast. Now, there's a new class of problems, which here is called hybrid inverse problems. As opposed to multimodality, hybrid inverse problems tries to combine two modalities through some physical coupling. There's physics coming to the rescue that will couple a modality with high contrast with another modality with high resolution. Okay, so hybrid, we heard the word hybrid yesterday used not for the hybrid inverse primes that I'm going to talk about, but for the multimodality inverse primes that Simon mentioned. So there is some discrepancy in the literature. So some people have talked about multiphysics as a good way to represent these new inverse problems. Multi-waves also is another name. Okay, so I'm switching from hybrid to multiphysics inverse problems. But the idea there is that we really want to use two modalities, one that will display the high contrast that we need in order to see the tumor, and one which is high resolution that we need in order to see the tumor early on. All right, so in this talk, I will mostly focus on ultrasound coming from ultrasound, and I will also mention MRI very briefly, but mostly coming from ultrasound. And the high contrast will mostly come from optical or electrical properties, as in Simon's talk, although the high contrast can also come from elasticity. All right, so that's the roadmap, if you wish, of what we want to talk about here. All right, so now the hybrid inverse problem has typically two steps. A first step is really what Li Hong presented to us yesterday. In the first step, we want to acquire those internal functionals that I've mentioned in the title. And those are the pictures that you saw in Li Hong's talk. Li Hong looked at photoacoustics, showed us how we could transform acoustic measurements into internal reconstructions. All the pictures he showed us were internal reconstructions. The reconstructions that he showed us were not the reconstructions of the parameters of interest. They were functionals of the parameters of interest. And so an inverse prime consists of reconstructing those parameters themselves from the functionals. And that's the second step. Okay, so the second step, I'm not going to talk too much about the first step, which you saw in Li Hong's talk yesterday. I really would like to focus on the second step, which is once you have acquired those internal functionals, you don't quite have the quantitative information that is necessary for you. Is the absorption coefficient 1 or 1.2? We don't have access to this at the level of this first step. We have to solve a second inverse problem from those internal functionals, and that's what I would like to talk about. So I will present several inverse problems where we have acquired internal functionals and we want to reconstruct physical parameters describing the tissues. And so the theory of those hybrid multi-physics, multi-wave inverse problems, the theory is based on what is it that we can determine uniquely, what is the stability that we can get, and hopefully we will get a stability that is much better than logarithmic, otherwise we would not get the resolution that we're interested in. And there's something that's interesting along the way as we prove uniqueness and stability. There's a question of how you probe the medium, the tissues that we're interested in. What I mean by probing is, should we send photons this way? Should we send photons that way? Should we send photons from here? There are various ways that we can illuminate our target area. And depending on the illumination that we choose, the solutions of the PDs might satisfy properties that allow us to get uniqueness and stability or not. Okay, so there's an interesting mathematical question, which is how much are the uniqueness and stability results affected by the illuminations that we choose. So I will show you some mathematical results in this direction. There's much more to do here. All right, so let me show you some models now so that we can discuss more concretely on some on using some equations. So the model that was presented by Simon for optical tomography is this diffusion equation. U will be a density of photons, gamma will be a diffusion coefficient, sigma will be an absorption coefficient. And the internal functional that Li Hong presented to us yesterday, what is it that he plotted yesterday? What are all the images that we saw yesterday? That was this H here. The H is not a parameter that is a constitutive parameter of the tissues, rather it's a functional of these constitutive parameters. So for photoacoustics, I will come back to it a little bit, but photoacoustics looks at the amount of photons that are absorbed. What are the photons that are absorbed? That depends on how many photons made it to a point. That depends on the absorption rate at that point. So sigma times U is how many photons got absorbed. And then you might remember that the photoacoustic effect sends acoustic signal. So there's a transfer, there's a physical coupling between this absorbed radiation and the amount of sound that is being emitted. Gamma, the Green-Eisen coefficient, is that coupling effect. So physics comes to the rescue thanks to gamma here. Physics has coupled radiation to the propagation of ultrasound. So at the end of the first step of the inverse problem that Li Hong mentioned, we have access to H. Okay, now there's three parameters that we don't know. There's gamma that we don't know, there's sigma that we don't know, there's this big gamma that we don't know. And if we knew them, we would know U. Okay, so there's really three parameters that we'd like to reconstruct. And what type of probing mechanism do we have? Well, we can play with the illumination. We can play again with how we send photons into the tissues. So how many illuminations, how many boundary conditions should we use? And how should we use them in order to reconstruct as much as possible about those three parameters? That's the first question. How stable are the reconstructions? And how much does the uniqueness of the reconstruction, if uniqueness is there, and how stable are the reconstructions, how much does this depend on the choice of the illuminations? Okay, that's a first inverse problem, hybrid inverse problem that we would like to look at. This hybrid inverse problem that shows up in quantitative PAT also shows up in magnetic resonance elastography. The only difference is that the measurement is not gamma sigma U, but U itself. It changes the problem a little bit, but the mathematical apparatus is very similar. So if you've seen very interesting results obtained in magnetic resonance elastography, it seems to be a very, very promising technique. The mathematical aspects related to the reconstruction of the physical coefficients from the internal measurements, the mathematical apparatus is very similar to what I'm going to talk about for quantitative photoacoustics. All right, so to briefly remind you of what the photoacoustic measurement is, or what the modality is, how do we acquire this H here before we move to the reconstruction of the parameters themselves? How do we acquire H? Well, we acquire it like this. We send a pulse of photons into tissues. The photons propagate very quickly through the tissues, and some of them get absorbed. The photons that get absorbed generates a very tiny increase in temperature. That tiny increase in temperature corresponds to some thermal expansion. The thermal expansion, like we speak, generates some acoustic waves. The acoustic waves propagate. We have ultrasonic transducers, detectors at the boundary of the domain that measure this pressure field as a function of time and space. So we have 3 dimensions of measurements for 3 dimensions of density of absorbed photons. Okay, so we reconstruct this first inverse wave problem, which Li Hong presented yesterday. We have an image formation through the inversion of a wave equation. What we obtain is H. Okay, so the first step was what Li Hong described yesterday. That's also what is on this cartoon. And the second stage is, once we have H, what can we reconstruct about the coefficients? Okay, and so Li Hong presented some great results yesterday. This closer to here, this Paul Beard's lab that has also obtained very interesting results in photoacoustics. So that's a modality that seems to be working extremely well, at least in the lab, and might make it as a clinical modality soon. There are other models, PDE models, that we can consider and for which we can ask ourselves very similar questions. Quantitative path photoacoustic, what I presented earlier, use photons. You really send near infrared, almost like light, into tissues. Now there is a slight issue with light, which is that it propagates through tissues, but it still gets attenuated. So instead of sending light, what we can send is low frequency radiation, electromagnetic waves, into tissues that will propagate a little deeper. And we cannot model those waves by radiative transfer equations. They don't scatter. We have to use a Maxwell model, and Maxwell is a little more complicated than the scalarized Maxwell, which is Helmholtz. So let's assume that we model this propagation of electromagnetic waves by a Helmholtz equation. We then have propagation in the absence of any absorption, and then some of the waves get absorbed because of this conductivity term here. And the internal functional that we now measure from that reconstruction, from the ultrasound that we measure, the functional is also the amount of absorbed radiation. This is not a number of photons anymore. This is just an energy, electromagnetic energy, U squared, multiplied by the absorption coefficient. That's the rate of absorption of the electromagnetic waves. So our functional now is H. We know H. Can we reconstruct sigma out of measurement of H, knowing that U satisfies this equation? The answer is yes. We have a result also of reconstruction of sigma from H for certain values of G. There we need to choose the illuminations appropriately in order to have a uniqueness result. So that's a result I'd like to present very briefly. There's another way that physics comes to the rescue to couple optics and ultrasound. That way is called ultrasound modulation optical tomography, or is also called acousto-optics. Let me show you a picture of what we are doing here. We don't measure acoustic signals anymore in ultrasound modulation. What we do is, as the name mentions, we modulate the tissues by some ultrasound transducer. You send some ultrasound into the tissues. When we send some, say, plane wave through the tissues vibrate a little bit. The density of scatterers changes as the ultrasound propagates. So if you send light into those tissues that are modulated, the light on the other way will also be modulated, will be affected by the ultrasounds that we send into the tissues. If you model this, something that we did with John Shotland a couple years ago, if you model this, then the internal functionals that we can get out of this experiment, and I'm not going to show you how we obtain this, is the following. We have the same equation for the photons. The same photons as before propagate through your tissue with a lot of scattering. We have the same diffusion equation for the photons. But now the functional, instead of being linear in U, is quadratic in U and involves the gradient of U. That makes the reconstructions, at least the mathematical analysis of this equation, much more complicated. So we have a functional now that is no longer proportional to U or U squared, but also proportional to the gradient of U. Okay, so that's another hybrid inverse problem, multiphysics inverse problem that I'd like to mention to you, show you a little bit of theory about how the reconstruction of these coefficients behaves. Okay, so that's those are the three hybrid inverse primes, three selected hybrid inverse primes for which we have some theory, at least partial theory, that I'd like to present now. So typically we have some unknown coefficients, some unknown solutions to the elliptic equation, and we have some known models, and we have some known internal functions. Okay, so that's what we start from. We have unknown coefficients and unknown elliptic solutions. There is quite a few unknowns, so you try to eliminate as many unknowns as possible. That's something that's classical. Sometimes this step is easy. Sometimes this step is a little harder, but okay, that's what you start from. And then there is a second typical step in those inverse problems, which is the following. If the elliptic solution satisfies some qualitative properties, the qualitative property might be there's no critical point. You have an elliptic solution, gradient u does not vanish. That's the type of qualitative properties that I'm talking about. If the solution satisfies this qualitative property, then we can obtain a unique and stable reconstruction of some of the coefficients. We don't always have uniqueness, but as soon as we have uniqueness, we're not very far from having stability as well. Okay, so there's a second step, which is under some qualitative assumptions on the solutions of your elliptic primes. These were all elliptic primes that I mentioned to you. You can replace that by a transport equation, but all the models that I presented so far were elliptic equations. If the solution satisfies some qualitative property, then we get a unique and stable reconstruction. And now there is the choice of, is the if satisfied, are the qualitative properties satisfied? And that's where we need the boundary conditions, the choice of boundary conditions. And that's where we can choose our boundary conditions G in an appropriate manner. Can we choose G in an appropriate manner? Are there some G's that exist that allow us to obtain the properties that we want? The answer is yes, but it's not so easy to prove it. And we need qualitative properties of elliptic solutions. These are elliptic problems with non-constant coefficients. How do you analyze that? You want to have solutions that give you qualitative information about elliptic solutions with essentially arbitrary coefficients. And the way the Calderon problem has been solved is by the use of complex geometric optic solutions. And we also wanted qualitative properties of solutions in order to solve that the Calderon problem. So here the CGO solutions will again be the mathematical apparatus which will come to our help to show that indeed we can construct well-chosen eliminations so that the qualitative properties of our elliptic solutions are satisfied. Okay, so that's the roadmap of all the problems that that I've looked at so far. All right, so let's come back to quantitative photoacoustics, which again is very similar to magnetic resonance elastography or transient elastography. These are relatively close cousins mathematically. So we have three coefficients that we don't know: the diffusion coefficient, the absorption coefficient, and gamma. Okay, this is the second stage of the what Li Hong mentioned yesterday. Li Hong plotted H, and now we want to go beyond that and try to reconstruct the coefficients in a quantitative manner. So we have, again, those coefficients that we don't know, and we have the measurements H. And we can use the boundary conditions, which here for simplicity are just Dirichlet conditions. That's to our choosing, and we'd like to choose them in an appropriate way. So let's assume that we have two illuminations. We send photons this way, we do the reconstruction that Li Hong presented. We send photons another way, we do the reconstruction that Li Hong presented. From those two boundary conditions, we have two internal functionals that were acquired, again, in a non-intrusive way. Let's define this vector field here, which is the gradient of H2 over H1 up to some decoration. Okay? That's the important aspect. Gradient of H2 over H1, which, as you see, is gradient of U2 over U1, where U2 and U1 are solutions of that elliptic equation. So this vector field is important for us. If the vector field does not vanish, and let's assume that it's bounded, strictly bounded from below by a positive constant. If that vector field that we have constructed from our data does not vanish, then we're in good shape. We're in good shape in the sense that we will be able to reconstruct two functionals. But we are in bad shape in the sense that we are not going to be able to reconstruct the three coefficients that are interested in. So let me show you the result. If we know H1 and H2, and the vector field associated to those two measurements is nice in that way, then you don't need to acquire additional measurements. Any other measurement that you would acquire. What is another measurement? Another measurement is this. You choose another G. So you've done this, you've done that, now you do this. Okay, and you acquire yet again the measurements associated to that third measurement. What this result says is you don't need to acquire that measurement. I already know the answer before you give me the information. The two measurements that were acquired thanks to that one and that one, those two measurements uniquely determine the whole measurement operator that you can acquire, the whole measurement operator which to G associates H. So that's a bad result. There's no need, at least in the absence of noise, there's no need in acquiring a third and a fourth and a fifth measurement. The two measurements that we have acquired at the beginning are enough to describe the whole measurement operator. So that's bad news because we can only play with two internal informations, and there's three coefficients that we want to reconstruct. So that starts as a relatively negative result. The positive result is that there's two functionals of those three unknown coefficients. There's two functionals, and those functionals are uniquely determined by the two measurements that we have acquired. Okay? So that's the result. There's two functionals that can uniquely be determined. And once you have those two functionals, you can actually close the loop and get those measurements again. So this is equivalent to knowledge of the full measurement operator, which is equivalent to knowledge of those two functionals. And that's all you can reconstruct from QPath. So I don't know how positive or negative it is. When you look at this type of function, if U was not present, then all you could reconstruct was gamma sigma, and that would be it. You would get gamma sigma, and there would absolutely be no way that you could get information about gamma. Because U actually participates in the internal measurement, U depends on gamma, and so there's a chance to get gamma. And so the result is these are the two functionals. It's not only one functional, but actually two functionals that we can reconstruct about the unknown coefficient. So that's a relatively positive result. So what do we need in order to reconstruct those two functionals? We need these to hold, and that's the if. We need well-chosen boundary conditions, measurements. You really need well-chosen boundary conditions in order for that vector field to be positive. Okay, and what does it mean? The vector field gradient of U2 over U1. U2 over U1 is actually a solution of an elliptic equation. So you need the gradient of U2 over U1 to not vanish. That's exactly what I'm saying. You don't want critical points of an elliptic problem. Okay, I'm going to show that to you in a second. All right, so the proof is relatively simple. The elimination that we need is relatively simple. There's an equation for U1 which you multiply by U2. There's an equation for U2 which you multiply by U1. You subtract, you shake, and at the end of the day you get an equation for chi-squared, which is a transport equation involving that vector field that I just mentioned. Okay, the vector field that I mentioned as a vector field for which I don't want vanishing points. If that vector field does not vanish, then this transport equation is a well-posed transport equation, and that allows us to reconstruct chi-squared, where chi is that object here, which is positive. Okay, so we have a transport equation to solve. Once we have solved the transport equation, there is a direct expression for Q, which is given directly in terms of the measurements. So those two functionals are easy to reconstruct from the measurements. It's not a very difficult result. And then you can prove that once you know those two functionals, you can determine the whole measurement operator. Okay, so there's a few lines in order to do this. Okay, but there is an if here, which is relatively important, which is that we need to be able to solve that transport equation. If that vector field vanishes too often, we won't get the uniqueness of that solution here of the transport equation. We are after uniqueness results. And we certainly will completely lose stability if the vector field becomes too nasty. Okay, so if we have a nice vector field, then we have reconstructions of chi and q. Moreover, that's the positive result that maybe we want to remember. We have access to chi and q now. if one of the coefficients, gamma, sigma, and big gamma is known, let's say the Green-Eisen coefficient, typically the Green-Eisen coefficient is assumed to be constant in applications. Whether that's correct or not is another issue, but gamma is often assumed to be constant. If gamma is known, then lil gamma, the diffusion coefficient, and sigma, the absorption coefficient, are then uniquely determined by the two measurements. Okay, so that's the positive result here. If you assume that gamma is known, then those measurements, sigma times u, two measurements of the form sigma times u uniquely determine gamma and sigma. That's probably the main result that we obtain here in this field. And once you have these reconstructions, you can prove that the reconstructions are stable. And that's not very difficult. You have to look at the stability of a transport solutions. Now, a forward prime, you have a transport equation, we have a vector field. Now, if you make other measurements, the vector field will be modified a little bit. And the question now is how stable the reconstruction of a transport solution is with respect to changes in the coefficients of that vector field. Okay, so there are various ways that you can analyze that transport equation, and you can get stability estimates of Lipschitz type or of Hurlder type. Let's not go into the details of what these stability estimates are, but we have relatively reasonable stability estimates coming out of the analysis of what? Of just this transport equation. Okay? And then if you want to look at the stability of Q, well, you have an explicit expression for it. So getting stability reconstructions, stable reconstructions, almost comes from free if you have this if satisfied. Okay, so those are the results for quantitative photoacoustics. And the contrast might not show up very well, but this is these are simulations in 2 dimensions of a relatively jagged, I hope you can see that there's some blue and there's some red, so relatively jagged diffusion coefficient, relatively jagged absorption coefficient. In the absence of noise, the reconstructions are perfect. And in the presence of noise, the reconstructions degrade a little bit, but we still get extremely good reconstructions, and the details here and there and at the boundary of the domain are the same. We have now internal information, so as opposed to diffusion tomography, diffuse optical tomography, where reconstructions are good at the boundary and deteriorate very quickly inside because high frequencies do not propagate from the inside to the measurements. Here we have internal measurements that give us good resolution throughout the domain. Okay, so mathematically, those hybrid inverse primes have all the good properties that we want. There's high contrast and there's high resolution. I'm going to show it in the next slide. That's a fair point. So hold on to, I'll come back to Adrian's question for a slightly different model. So let's look at quantitative TAT, which is now a slightly different elliptic model where we don't know this gentleman here, the conductivity coefficient, and what we have access to is sigma times u squared. Okay, so there's a result that says that, again, provided that the illuminations are chosen well, and there's an open set of illuminations that works, provided that you choose the illuminations well, illuminations is how you derive the electromagnetic signal from the boundary, provided that you choose this object well, then we have a unique reconstruction and we have a stable reconstruction. So if 2 measurements agree, then the 2 conductivities agree, and with appropriate norms, which are Sobolev norms of sufficiently high S, all the results require enough regularity. That's the problem. In all these theories, because we use CGOs, we need regularity. So we might not be so happy about what the Y is. It's HP for P greater than N here. Okay. So in that norm, we have Lipschitz stability. It's perfect reconstruction. So why they are the same here? Yes, they are the same here. So now there's a good argument why here they should be the same. Over there we solve the transport equation. There might be some derivatives floating left and right here. Let's assume that sigma is small and that G is a plane wave and that this plane wave is consistent with that. Then what we see is that U squared is 1. And so H is sigma. So if there was no diffraction, we would get that U would be 1, and then the measurement would be sigma. So we kind of expect some Lipschitz stability. Okay, so all we have to deal with is precisely the diffraction effects that arise in that Maxwell equation. And so to come back to Adrian's question, what do we have to do? What do we get if we don't account for that diffraction effect? This is what we get. This is sigma. Okay, so again, I'm sorry, the contrast might not be so good, but this is what H would look like. That's sigma, this object, multiplied by u squared. I think the illumination comes from the left. It's just a plane wave coming from the left, but sigma is relatively large and hence generates a fair amount of diffraction. And so if you plot H, that's what you get. You have to clean that in order to reconstruct sigma. So there are various ways of cleaning it. And if in the absence of noise, the cleaning is perfect. In the presence of noise, the cleaning is not as good. But we still get some relatively good reconstructions, and indeed they are stable. Okay. All right. So that's the that's what happens for a quantitative PAT and quantitative TAT. Now there's another class of primes that are related to ultrasound modulation, which are mathematically harder. Okay. So far, what I presented, the elimination was relatively simple. What's hard is to prove the qualitative properties that we need about the vector field, the fact that the vector field does not vanish. Hopefully, I'll have a minute at the end to show you how that works. But before I look at that, let me show you another problem where the eliminations are either easy and then the prime is hard, or the eliminations themselves are hard. All right, so let's look at that prime where now we have grad u squared in the measurements. The square doesn't matter. You could obviously take the square root of everything here. But here we have a gradient u that shows up, and that makes the mathematical analysis a lot harder. So let's assume that we have measurement of this type. I've neglected absorption here. Again, we only have a conductivity coefficient, and we have a measurement which is conductivity multiplied by grad u squared. Now, what you might think is that the elimination of gamma is completely trivial. Gamma is nothing but h divided by grad u squared. Gamma is h divided by grad u squared, so we just replace gamma by h divided by grad u squared, and we get an elliptic model where p is equal to 0 here. Okay, and so you might think this inverse prime is nothing but solving a nonlinear equation. That's true. The problem is, what are the properties of that nonlinear equation? Well, p is equal to 0 in our problem here. It's the so-called zero Laplacian. And if p is between 1 and infinity, this is a nice elliptic problem associated to a functional that's strictly convex. So there's no difficulty in proving that the solution to that problem is unique when p is greater than 1. When p is equal to 1, I refer you to what Adrian has done, this becomes much more difficult because the ellipticity is lost. There's one direction in which you lose ellipticity. You had ellipticity in two directions, then you have ellipticity in one direction only. So n dimensions minus 1. So your problem becomes degenerate, and that's what Adrian has done with Alex Timonov and Alex Tamasan. Okay, so that's this inverse problem shows up in CDII and MRI90. Degenerate elliptic. Okay, so if you go from elliptic to degenerate elliptic, if you push further, you have to be hyperbolic, and that's actually the case. The problem becomes hyperbolic. So this inverse problem, when you look at it as a PDE model, actually becomes hyperbolic. So hyperbolic, we know that we cannot deal with hyperbolic primes with only Neumann, with only Dirichlet data. We need Neumann and Dirichlet data. We need two boundary conditions. So let's assume that the current is known. So that's a zero Laplacian with Cauchy data. Now I add a little bit of information. Not only do I assume that H is known at the boundary, but I also assume that the current is known, okay, which is relatively easy to measure. That's what is measured in optical tomography anyway. And then if you shake that equation and rewrite it as a nonlinear hyperbolic equation, what you observe is that the reconstructions, let me directly move to the stability result and uniqueness result. What you observe is that if you take the boundary, there is a piece of the boundary that is so-called space-like. There's only a piece of the boundary from which we can get information. Take a subset of that piece of the boundary that's space-like, and take the domain of influence of that boundary, if you know what I'm talking about. Then on that domain of influence, we get stability. And as theta here gives us the distance from the domain of influence to the boundary of the domain of influence of the space-like component, the stability estimate degrades. Let me just show you a picture. Let's assume that we have a sphere, and let's look at this light cone. Of course, it's a hyperbolic prime. There's light cones everywhere. Let's assume that we have a metric which is a metric for which time is like the z direction here. So that light cone essentially gives us an intersection of the light cone with the sphere, gives us a part of the boundary, which is a part of the boundary which I'm going to call space-like. Now let's pick a small part inside the boundary and let's look at the domain of influence of that part. That's the green shaded area. I'm not sure you can see the green, but that's a cone which is here. Okay, that's this part of the cone. Inside that cone, we get stable reconstructions. Outside of that cone, we don't. Okay, so the problem becomes, it looks like a simple equation to look at. It turns out that the stability is only available on a piece of the domain. Okay, so I'm going to leave it at that because I'm running out of time. But this problem that looks relatively simple actually gives us stability only in part of the domain. Okay, that's something that has to be verified numerically. I think Otmar has some numerical simulations that seem to validate this kind of picture, but this is something that we expect. So what can we do about this? Can we restore stability? Yes, there's a way to restore stability, which is to look at multiple measurements. So that's something that's a little strange, but let's assume that, let's look at that problem again. I had one unknown and I'd made one measurement. I had one internal measurement. Let us assume that instead of making one measurement, I still have one unknown, but I make a lot more measurements, j squared measurements of the form grad u I dot grad u j. Let's say alpha is 1/2. So that's gamma, instead of being gamma grad u squared, it's gamma grad u I dot grad u j. Let's assume we have access to this great wealth of measurements. Now, it turns out that the elimination now becomes difficult. We have gamma that we don't know, and there's a vector field associated to it. We'll have all these s's such that si dot sj is those measurements. So those are also unknowns. And it turns out that you can eliminate f by looking at those problems and get an equation for s, which turns out to be a redundant system of ordinary differential equations for s. Then you can solve that and you get a uniqueness result. So there is a uniqueness result associated to this. So the upshot of this, the morality of this is that if you're stuck with a problem for which you don't have stability for one measurement, just acquire more measurements, and sometimes that will help. Okay? That seems to be the case. We would like for one object to reconstruct to acquire one measurement. Very often we cannot do this. For one object we can reconstruct, sometimes we have to acquire a lot of measurements, and that allows us to restore stability. What is the optimal number of measurements we have to make? I don't know. Okay? But we have at least relatively systematic ways of acquiring more measurements and get good stability, good uniqueness. I'm not going to mention that, uniqueness and stability results. Now that you have all these measurements available to you, if you have these measurements and you make an error in the W1 infinity norm, then you will get reconstructions also accurate in the W1 infinity norm. Okay, that's the results that we'll. Okay, I don't have the time to tell you where the ifs are coming from. Well, all I'd like to mention is that we need qualitative properties of the elliptic solutions to be satisfied. What are those qualitative properties? We don't want critical points in QPAT and in transient elastography. That should be TE. Okay? Sometimes we want a contraction of an appropriate functional. That's what happens in QTAT, the reconstruction of sigma. Sometimes we want a Lorentzian metric to be a real Lorentzian metric. Okay, so that's what I just mentioned. Sometimes we want, in that last problem, we want to eliminate vectors, and we need linear independence of gradients of elliptic solutions. How do we get the linear independence? All of these results, you can get them relatively easy in dimension 2 because there are some miracles essentially related to the fact that critical points are isolated in 2 dimensions, and so we can prove that they don't exist most of the time. But in dimension 3 and higher, the only available technology is based on CGOs, okay? The standard CGOs. You use your CGOs and you can prove that a vector field associated to CGOs is a nice vector field. And then that's what happens for non-perturbed media. And when you have a perturbed medium, the great thing about CGOs is that the perturbations don't affect the CGOs too much. So whatever qualitative properties you had for the CGOs in the absence of perturbations, you retain to a large extent in the presence of perturbation. Okay, so if the illuminations are close to traces of CGOs, which we don't know, if the illuminations are close to traces of CGOs, then we're in good shape. Okay, so we have an open set of boundary conditions that work, but we don't really have a very good characterization of what these illuminations are. Okay, so sorry I'm running a little bit out of time. hybrid imaging modalities, multi-physics imaging modalities, multi-wave imaging modalities, use physics to give us a coupling between a high-resolution technology modality and a high-contrast modality. Okay? All of them have this in common, and that's what we want in medical imaging. What are the issues? The issue is that typically the signals that we get, this coupling, is very weak, very small. That's what Li Hong mentioned yesterday. The amount of acoustic signal that we get is very minute, but we can measure it nonetheless. And when you can measure it, you're in a good situation that you can indeed hope, at least from the mathematical point of view as opposed to optical tomography alone, you can get both high resolution and high contrast. From the mathematical point of view, most of these problems allow us to get explicit or quasi-explicit reconstructions, solving classical linear or nonlinear transport, elliptic or hyperbolic equations, depending on the models that I showed you. The main difficulty is that we need all the time to have qualitative properties of elliptic solutions, like again the absence of critical points, and that's something that is very difficult to obtain from a theoretical point of view. And so the only tool that is available to us, this is a very general tool, generic tool that works most of the time. It's the tool of complex geometrical optics solutions. Okay, so that's where we are at the moment on this problem. Thank you.
Yeah, any questions? Yes, at the back.
What regularity do you require for sigma?
So for sigma, so there are several sigmas that were floating around. Let me just mention it here for the CGOs. That's really the bottleneck. We need, in CGO solutions, we have these unperturbed solutions that we then perturb with some Q that depends in a functional way on sigma. So we need to make sure that C is small in an appropriate norm. If you take a gradient of your solutions, the gradient of C will have to be small. The gradient of C will have to be small, knowing that C is a solution involving Q. So Q will have to be sufficiently regular so that the gradient of C is small in the appropriate norm. And that translates into some regularity on the sigma. All the regularity bottlenecks that we have come from us using CGOs.
That condition, it was like 3 pages before about the Wronskian of solution. Is it on here?
Here?
Yes. Is it actually that you really need n solution, or you can have more and the rank is at every point is n?
Oh yes, that's actually correct. Yeah, so we don't have n, we have actually more than that, and we need to make sure that the rank is of dimension n. Yes, that's correct. Yeah, and we can actually not do it. So we would like to do reconstructions with only n solutions. That's something we can do in even dimensions. In odd dimensions, we need n plus 1 solutions because CGOs are complex valued. And then on one set you use n of them, and another set you use n other solutions. So this is actually something that we have to deal with in practice.
One more question.
Okay.
So for the internal measurement you got, it's from boundary measurement, right? The first step is still from boundary measurement. So for example, for the photoacoustic, in one of the difficulties, you only have partial views. You only have partial kind of measurement. So that really cannot give you a very good quantitative internal measurement.
Yes, so step 1, which is what you're referring to, I assume done. I swept it under the rug, and here I wanted really to analyze how you could get from that step 1 to qualitative reconstructions of the coefficients of interest. Now, if H, let's look at this one here, is measured only in some piece of the domain, some part of the domain, then you're back to optical tomography. Wherever you don't have information, the singularities of the coefficients you want to reconstruct have to propagate where you have information, and the high frequency will have to be lost. So if sigma is 0 somewhere and H is 0 somewhere, if you don't have any absorption at some point, then in that area where absorption is equal to 0, you cannot reconstruct neither sigma nor gamma accurately. So it's it's absolutely true that we need H here to satisfy some nice properties. Now, to come back to the question of reconstruction from boundary measurements, if you acquire boundary measurements only in some piece of the domain, can we reconstruct the coefficients everywhere? Let's assume that we have H in only some piece of the domain. Well, that depends on the model. If you look at what happens in photoacoustic, we have to solve a transport equation. All you have to do is to solve characteristics. And so as soon as there is a characteristic that makes it to the boundary, that part of the domain can be solved accurately for chi. And then can be solved accurately for q, and then you will get information associated to this. So you will have some partial reconstruction. For the hyperbolic prime that I mentioned, you have stability only in part of the domain, but you don't care about what happens here. All the reconstruction in that part of the domain depends on the information that was acquired from that piece of the boundary and inside that cone. So there is a lot of locality related to those reconstructions. So the reconstructions give you some information also about how local the measurements can be, the H's can be. But if you don't have H accurately, everything breaks loose. Yeah, that's true.
Okay, so let's thank the speaker again.